Good morning, one and all. Welcome back to the video lecture series, Probability Theory Stochastic Process. This is Dr. P SREENIVASULU. Today we are going to see a problem on this wide sense stationary process. Now, previous classes we have seen wide sense stationary process means the random process x of t. If you consider the random process x of t, if you calculate the mean value, it must be constant. And if you calculate correlation, autocorrelation. Suppose there is a one random process, we can calculate autocorrelation. Suppose there is a two random process, we can calculate cross correlation. So this correlation is independent of time. Then we can say it is random process is a wide sense stationary random process. Now if you see this problem, if a random process x of t is equal to a into cos omega t plus b into sin omega t, it is given where a and b are uncorrelated. A and b are uncorrelated. So there is no any common information between a and b, and zero mean random variables having the variance sigma square. So the variance, it is not zero, but mean value is zero, and these two are uncorrelated. Find A, autocorrelation function, B, show that x of t is a wide sense stationary. So just now I discussed that a wide sense stationary means it can satisfy whatever the random process we have. If we calculate the mean value of random process, so the mean value must be constant, and if we calculate the correlation function, it is independent of time, or it is a function of some variable, dummy variable, tau, like that here. Now, first of all, you see the whatever the given data. The given data is x of t is equal to a cos omega t plus b sin omega t. And then he has given a clue, these two are uncorrelated, independent. So whenever the two events are independent events, we can write the formula. Generally, probability of A intersection B is equal to probability of A into probability of A. Similar fashion, here there is no correlation. So expected value of AB is going to be right expected value of A into expected value of B. So again, he has given that uncorrelated. So there is no any common information. So it is going to be 0. So the expected value of AB is equal to 0. And it must be have some variance. So that is going to be right. Expected value of A square is equal to sigma square A, that particular random variable A. And this expected value of B square is a sigma B square. Now, if you want to write this sigma B square and sigma A square separately, or you can write sigma B square is equal to sigma A square is equal to sigma square, same for our convenience, because he has not given the data. Now, first of all, you calculate autocorrelation function. Now we know the formula for autocorrelation function. Xx means same within the function Rxx of tau is equal to expected value of x of t into x of t plus tau. Now expected value of x of t. So you consider that formula, x of t formula, a cos omega t plus b sin omega t, whatever the given formula. And x of t plus tau means wherever you have a t, that t is replaced with t plus tau. Wherever you have a t, the t is replaced with t plus tau. So expected value of x of t into x of t plus tau. So you see a cos omega, t is replaced with t plus tau, and sin omega, again t is replaced with t plus tau. So it is the autocorrelation function. And then you can multiply these terms. You can multiply these terms. So we are going to get the terms are like this: a square cos omega t into cos omega t plus tau plus ab into cos omega t into sin omega of t plus tau plus ab into sin omega t into cos of omega t plus tau plus b square sin omega t into sin omega of t plus tau. So like that, we are going to be get the terms. Next, if you apply this expected value concept, you distribute this for all the terms, this expected value. Now you know what is the here expected value of a square and expected value of b square is sigma square, already we have seen. Now these two are uncorrelated. That's why the random variable a, and there is whenever there is a two signals, expected value of AB or expected value of x1 of t into x2 of t is independent. So it is going to be right individual calculation, expected value of x1 of t, expected value of x2 of t. So that's why you can apply that property. So whatever the first term you see, expected value of a square into cos omega t into cos omega of t plus tau. So you can write here expected value of a square into expected value of cos omega t into cos of omega t plus tau plus, and then expected value of AB into expected value of cos omega t into sin omega of t plus tau plus, again expected value of AB into sin omega t into cos omega of t plus tau plus expected value of b square and expected value of sin omega t into sin omega of t plus tau. Now it is going to be distribute like this. And then whatever the given data, based on that given data, we know that this expected value of AB is equal to 0. And wherever we have an expected value of AB and it is going to be substitute 0, so then remaining terms, if you observe, we will get two terms. One is the expected value of a square into expected value of cos omega t into cos omega t plus tau. Another one is expected value of b square into expected value of sin omega t into sin omega of t plus tau. Now, if you observe here, this expected value of a square, expected value of b square is equal to sigma square. Now, you take it is a expected value of a square, expected value of b square, sigma square is a common. And remaining, if you observe here, expected value of cos omega t into cos omega t plus tau plus sin omega t sin. Cos A, cos B plus sin A, sin. It is nothing but cos A minus cos B. So cos A plus B, you see here, cos A plus B, cos omega t plus tau minus cos B, cos omega t. Now these two omega t gets cancelled. So finally you have cos omega t. So this expected value of cos omega tau, it is cos omega tau, it is independent of time. So it is like a constant. You can write it as sigma square into cos omega tau. So finally, if you observe the random process of autocorrelation function, the random process of autocorrelation function is a independent of time. It is a independent of time. So it is a function of tau, some other variable. It is the one of the condition for wide sense stationary. It satisfies. Then if we see another expected value of x of t individually, the mean value, and if you distribute that one, expected value of a cos omega t plus b sin omega t, and expected value of a cos omega t is nothing but expected value of a into expected value of cos omega t, expected value of b, expected value of sin omega t. What is the expected value of a? It is a 0. What is the expected value of b? It is a 0. So finally is going to get 0. So expected value of x of t is equal to 0. It is like a constant. So the autocorrelation function is independent of time. The mean value is 0. That means constant. So hence, the given random process is a wide sense stationary. Now you see another problem is here. A random process is given as x of t is equal to at, where a is a uniformly distributed random variable. A is uniformly distributed within the interval 0 to 2. He has given the interval is 0 to 2. Find whether the x of t is wide sense stationary, WSS means wide sense stationary or not. Now you see that corresponding uniformly distributed function, you need to define that one. Because wide sense stationary means you need to calculate expected value of x of t. That must be some constant average value. And then if you calculate autocorrelation function, it is a function of tau. It is not, it is a independent of time otherwise. Now, what is the probability density function for uniform density function? So if you see that uniform density function, it has given that a is like variable instead of x. We are going to write f of a is equal to the interval he has given 2 to 0. That means b minus a. What is the b here? 2. What is the a? 0. So 1 divided by 2. Within the interval 0 less than or equal to a less than or equal to 2. And it is 0 otherwise. So whenever we are calculating this expected value of x of t, the formula is integral minus infinity to infinity, generally x of t and corresponding density function, and the density function with respect to a. The density function is here, suppose f theta of theta, we are going to write with respect to d theta. Fx of x dx, fy of y dy, like that, whatever the variable. Here, the density function is a, so you can write the limits for a as given for a. So the limits we are going to change from minus infinity to plus infinity to 0 to 2. And corresponding density function is 1 by 2. What is the x of t? X of t is at. He has given already x of t is at, and with respect to dA. It is equal to, you see here, if you integrate with respect to dA, t is a constant, you write outside, and t by 2 is a constant. Integration of a dA, a square by 2. Now you substitute that limits 0 to 2. And finally, we will get that is a t. So expected value of x of t is here t. It is not constant. It is a variable. So it does not satisfy our condition, wide sense stationary condition. And then second case, you see, the Rxx of tau is equal to expected value of x of t into x of t plus tau. So x of t, whatever the formula, you can write there, at into a of t plus tau. At is x of t, and whenever we have replaced t with t plus tau. And then, if you see, if you multiply these two, a into a square, that t into t plus 2. Now, if you see this t plus 2 into expected value of a square, you need to calculate that expected value of a square here. So, expected value of a square is equal to Again, we have a density function within the interval 0 to 2a square, whatever that one. We substitute, and if you finally calculate, again it is a function of time. So mean is not constant. This Rxx of tau is a function of t, hence the given random process is a wide sense stationary. The given random process is a wide sense stationary. So like that, I'm going to stop here. We will see the next problems also in the next class.